Okay, so today just basically learning how the gas law actually works, really, and we're going to apply it to calculate the amount of carbon dioxide produced in a reaction. So taking a few things, putting them together, stoichiometry, because you can never get away from stoichiometry, of course. Figuring out, using stoichiometry to determine limiting reactant. And then once we've figured out the stoichiometry of our reaction, figure out how many moles of reactant we need to make moles of product. And one of the products we're making is carbon dioxide. Once we figure out how many moles of carbon dioxide we produce, we use the gas law to determine how much of a volume that's going to take up. So stoichiometry and gas laws. I don't know if anything would be more fun. And then we're actually going to make an airbag, which for more or less obvious reasons, will be just a terrible airbag. So what is the overall gas law that we're going to be using today? Anyone give me basically what the ideal gas law is?
PV equals nRT.
Good old Pivner. Yep, PV equals nRT. So what do these all stand for? What does the P stand for?
Pressure.
Pressure, right. And what do we typically measure pressure in? What units do we use?
ATM.
Atmospheres, right. And what's the V?
Volume.
Volume. And what do we normally measure? What units do we use to measure volume?
Liters.
Liters, right. What is N, the small n? What does that stand for?
Number of moles.
Sorry?
Number of moles.
Moles of what?
Gas.
Moles of the gas, right. I made this mistake last night, actually. We were doing the experiment you'll be doing next week. We need to determine the actual moles of the product gas. Moles of anything else isn't really going to help us. Moles of a liquid isn't going to help. Moles of a solid isn't going to help. We need the moles of the actual gas being produced. So like for water, for instance, we're only interested in moles of water vapor. So in my glass here, I have water in 3 different states. I've got ice, so I got solid. I got liquid to drink. And then even though this is it's very cold, there's some small amount of water vapor that's being released from it. And so we would have to calculate the amount of moles of water vapor in order to determine the volume that vapor took up, of course. So what's T? What is this T?
Temperature.
Mm-hmm. Temperature. And when we're dealing with gases, what temperature do we use? What temperature scale do we use?
Kelvins.
Kelvin. Yeah, why? Why can't we use Celsius or Fahrenheit?
They aren't an absolute.
They are an absolute. Why is that so important?
Is it because you need a more specific number?
Well, any temperature is a specific number. I mean, right now the temperature in here is about 15 degrees. That's pretty specific, right? They're all specific numbers, but you were onto something when you said we need something that's absolute. Why is that?
Is it because it's not as easy to measure?
Oh, they're all fairly easy to measure. If I have a thermometer, I can measure I can convert that temperature to whatever scale I want. So it's not really the ease of measurement. What does the pressure from a gas come from? What is it about gas molecules that cause them to exert pressure? So if this is a cylinder, closed cylinder, and it has gas molecules in it. What is it about the gas molecules that cause them to exert pressure on the sides of the container? Have you learned about this? The kinetic theory of gases?
Isn't there movement?
It's their movement, exactly. So what is it about their movement that actually causes pressure to be exerted? When is pressure exerted by a gas molecule?
By temperature or?
It increases with temperature. That's true. But what is it actually happening with the gas molecule that makes it exert pressure on the sides of the container?
It's moving faster. It's pressing against the
It's
object.
pressing against it. Exactly. That's it. So these molecules actually have to hit the side of the container in order to exert pressure. If they weren't hitting the side of the container, there would be no pressure, even though there would be gas molecules in there. And so the gas molecules actually have to be moving in order for them to hit the side of the container. And so if they stopped moving, there'd be no pressure. But at what temperature is it that molecules stop moving?
Zero kelvins?
0 Kelvin, exactly. So because the pressure is directly related to the movement of the molecules, any temperature above 0, there's going to be some slight movement of molecules, and so some small increase in pressure. And that's why we have to use Kelvin. We can't use Celsius or Fahrenheit for the basic reason that they have negative temperatures. And there's no such thing as negative pressure or negative volume, or, right? There's no such thing as that. It can be 0, but it can't be negative. And since it's all based on movement, and the only scale that is absolute from 0 to whatever it gets to is the Kelvin. That's why we use Kelvin with gases. So what is this R? What's that thing?
The universal gas constant.
Mm-hmm. And what does it do, really?
It links all the units together, or like allows you to cancel them all out.
I couldn't have said it better myself. Exactly. It relates atmospheres and liters and moles and temperature. It relates all of them together. So today, we are going to be looking at the relationship between moles and volume. So that means that how are we going to determine if P doesn't change and T doesn't change? What does that mean for our relationship between moles and volume?
That means that V1 over N1 equals V2 over N2.
Right, it means they're directly related, right? So we can basically take the others out of the equation. But if what we're going to do is we're going to define N and see what happens to V. So basically, we are going to determine what N is by calculation. And then we're going to have to find out what the V is going to be. So what we're going to do, basically, is clear. So I'll put my PivNert back in here again. we want to see what V is. So we're just going to basically divide each side by P. So this is going to be unknown, and this is going to be known. So what we're going to do is, actually it's going to be the other way around. We need to define what N is, because we're going to, our bag is going to be 1.2 liters. So actually it's the other way around. I apologize. We're going to need to define what N is. So N is going to be equal to, divide both sides by PV, and it's RT divided by PV. Oh, sorry, no, PV divided by RT. Man, I'm just having a really hard time today. We want to isolate N by itself. PV divided by RT. There we go. So our volume is going to be 1.2 liters. What's the pressure going to be? How do we define what the pressure is? How do we know what the pressure is?
The air pressure?
Mm-hmm. How do we find it out? I don't have a air pressure monitor in my house. I doubt anyone else does. So how are we going to determine what P is?
Google?
Hmm?
Google?
Yeah, basically. Just Google air pressure wherever you are right now. And you'll find it's going to be pretty close to 1 atmosphere. And generally, the pressure is given, because this is America, in inches of mercury, which isn't terribly helpful because R doesn't have inches of mercury. You can look up an R with inches of mercury, but it's not the R we use. How do you go from inches of mercury to atmospheres?
Inches to centimeters to millimeters to ATM?
Man, there you go. Yeah, so we convert inches to millimeters, and there's 25.4 millimeters per inch. And then how many millimeters of mercury in an atmosphere?
760?
There you go. Man, you're all over this today. 760 millimeters of mercury is equivalent to 1 atmosphere. So you'll find that whatever your atmospheric pressure is where you are, it's going to be pretty close to 1 atmosphere. Because if it drops dramatically or goes up dramatically, you would see a huge difference. I mean, the weather's kind of cloudy, overcast, and a little windy. So the atmospheric pressure is probably a little bit lower than 1 atmosphere, but it won't be by much. So we will have to figure out what that is before doing our calculations. Now, when it comes to T, I mean, how are we going to measure T?
Thermometer?
Yeah, we got a thermometer in our kit, right? So we just take out our thermometer. And what's the thermometer we have in our lab kit? What are the units of temperature on the thermometer?
Celsius?
Mm-hmm. Yeah, they're in degrees Celsius. So what are we going to have to do with that to convert it to a temperature scale we want?
You just add 273.15, I think, right?
That's right. So our temperature in Kelvin will be the Celsius temperature plus 273.15. And then R, we're just going to plug in R, 0.0821 atmosphere liter mole kelvins, which is still bizarre. And then once we plugged all that in, we'll determine number of moles of gas. And the gas we're going to be making today is CO2. So in order to determine how many moles of CO2 we're going to need, we obviously need to know what the reactions are, and then we need to balance them. Okay. So has anyone else been in an accident where the airbag's deployed? Am I the only one?
Not me, no.
It hasn't happened to anybody else, which is good. I mean, I don't want any of you in a car accident, but my family got hit when we were in downtown LA a couple of years ago. And believe me, these airbags deploy quickly. I mean, so fast you don't even realize it happened. So we got hit, we got T-boned. The airbags deployed, and by the time you realize what happened, they had inflated and then deflated again. And so it's super, super fast. And the reaction that takes place inside the airbag is sodium azide decomposing. So what's a decomposition reaction?
When you have one whole molecule that separates into two.
Right, exactly. So we have a synthesis reaction. We're making one molecule or making out of two or more. And when it's a decomposition reaction, it's basically falling back apart again. Now, sodium azide is not very stable. And the reason is this is the molecule. And the whole thing has a negative charge. So sodium is plus, and then we have two azide anions. And so how many electrons should there be in an azide anion? Total electrons. How many valence electrons are we dealing with here? How many does nitrogen typically have? Oh man, everyone's forgotten that already. No, Jean, you're close. You're missing one.
3.
Nitrogen does not have 3 valence electrons. What group is it in?
Oh, 5.
It has 5. Right, so we have 3 nitrogens for 15 electrons. And remember, it's charged. There's a negative charge for 1 more. So it's a total of 16 electrons. So we've got 2 bonds already. So that takes out 4. So we're left with 12 electrons. So, and then remember, each one wants how many? Each nitrogen wants a total of how many electrons to be happy?
3.
How much, when they have a full outer shell, how many total valence electrons will each nitrogen have?
8.
8, right. So they all want 8. So the easiest way to do that is just to have double bonds there, and then 1, 2, 3, 4, 1, 2, 3, 4. That way everybody has 8. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Every nitrogen now has 8 electrons. But there's a problem. Let me fix this up. What is going to be the formal charge on the nitrogen in the middle? You remember how we do formal charges?
It would be +1.
It would be +1, exactly. Because, why is it +1?
Because it has 4 electrons, and then it actually has 5 valence electrons.
Right. So it can only claim, it has a total of 8 electrons, but it can really only claim 4 of them for itself because they're sharing, each nitrogen is sharing a pair of electrons in each bond. So this nitrogen has 4 valence electrons and has a positive charge. What about the nitrogens on the outside? How many valence electrons do they have?
6.
They each have 6, right? Because they have 4 electrons from their lone pairs, and they have another 2 from the bonds for a total of 6. Well, nitrogen's only supposed to have 5, so it actually has 1 more electron than it typically does. So these two have negative charges. And there's another way we can draw this, right? There's a resonance structure here. And the resonance structure would be if this pair of electrons moved here, and then this pair moved here, and then this pair moved there. So we would have so now we have this other way of looking at it. So so this one in the middle still has a positive charge because it still has only 4 electrons. What about this nitrogen? What's the charge on that nitrogen?
0.
This one is 0 now. And what about the one on the end?
-2.
It's -2, right? Because it now has 7 valence electrons and it should only have 5 for -2. So each of these is possible, but notice each one of them has negative charges right next to positive charges. And we know that that's extremely unstable. So basically, azide is just dying to get back to a more stable conformation. And the more stable conformation is if for 2 azides to come together and form 3 nitrogen molecules. Because nitrogen is pretty much as stable as it gets. As we know, nitrogen with a triple bond is super, super stable. Each nitrogen has exactly 5 electrons it can call its own. It has 8 total, super, super stable. And so azide is extremely unstable. And so when you basically give it a small electric charge, that's how it explodes. Give it just a small electric charge, the whole thing just goes boom and turns this solid azide. It's actually a solid. Because it's a charged molecule. What kind of molecule would this be? We have a sodium is a cation, and azide's an anion. What kind of molecule is that?
Covalent.
Nope, it's the other one. Remember, they're charged molecules. So it's not a covalent bond that's holding them together. What kind of bond is it?
Ionic.
It's ionic. It's an ionic solid. So it goes from just a small, tiny amount of ionic solid to a big amount of covalent gas. So that's the reaction that takes place. And it happens in just in like a few milliseconds. I think it's like it only takes about 20 milliseconds for the ionic solid to inflate the bag by turning into gas. And obviously it's pretty important that it does that rather quickly, because in a car accident, things happen kind of fast. So you want the reaction to happen quickly. But here's the reaction we're going to be doing today. Now, number 1, what are those 2 reactants? I have a solid and I have AQ for aqueous. What are those 2 things?
Sodium bicarbonate and acetic acid.
Mm-hmm. Exactly. So I have 1 mole of sodium bicarbonate plus 1 mole of acetic acid, and then it makes this. So you see that the arrow sort of points out this way. What it does is make this. So what are these two things? What's this and that? What's H2CO3 aqueous? Did you not read the instructions, the lab write-up? So if this is bicarbonate, what do we call CO3?
Carbonate.
Carbonate. So you remember how we name acids? If we have carbonate acid, what do we call it?
John said in the chat, carbonic acid.
Yeah, Sean's very clever. It is. It's carbonic acid. That's the acid that keeps your blood the proper pH. With the CO2 in your body dissolves in water and forms carbonic acid. What is this other thing? What's this?
Is it sodium acetate?
It is sodium acetate, exactly. So what kind of reaction is this? From 1 to 2, I have sodium and I have hydrogen. What happens to them? What kind of reaction is that?
Double replacement.
Man, you are killing it today. Yeah, that's exactly what it is. This is a double replacement reaction because the hydrogen basically takes the place of the sodium on the bicarbonate and forms carbonic acid. The sodium takes the place of the hydrogen on the acetic acid and becomes acetate ion, and sodium then basically swaps positions, being in a solid with bicarbonate to then being in solution with acetate ion. So, but we're not done, because even though nothing happens anymore to the acetate ion, we can take the acetate ion out. Because you see, we have it here and we have it here. So it doesn't continue the reaction. What does happen, though, is that the carbonic acid, forms H2O and CO2. What kind of reaction is that?
Acid base.
Sort of. It's also something else. Something more general. What kind of reaction was the sodium azide reaction we just looked at?
John says decomposition, so I believe it.
Everyone's just waiting for Sean to say the right thing. John, you should be teaching this class, man, I swear. Yeah, it's a decomposition reaction. And so this reaction is actually in equilibrium. So what is equilibrium? What's an equilibrium reaction? Have we learned about that? Or does anyone remember from way through their last class what that is?
Like balance?
It doesn't exactly mean balanced. That is a common misconception, that it means balanced. Because when you think of balance, it means that both sides are the same. And an equilibrium reaction doesn't actually mean that. You're close. I mean, that's sort of the way it's taught, but that's not really accurate. I'll sort of I'll let the cat out of the bag. Basically what it means is that that reaction goes in both directions. That this reaction goes in one direction and it goes in the other direction. So carbonic acid decomposes to form water and CO2, but water and CO2 also come together and form carbonic acid. The only difference is this reaction is much faster going in this direction than it is going in the reverse direction. So you see very little carbonic acid and you see more H2O and CO2. So it's in equilibrium, but that equilibrium favors the production of H2O and CO2 by quite a lot. And if we look at carbonic acid, it looks like this. And so when you have, we already know that oxygen is very electronegative, right? It's super electronegative. It is pulling electrons away from other atoms. And these two oxygens are even more electronegative than usual because there is another oxygen right here that's bound to the carbon. So this oxygen is pulling electrons away from the carbon, which pull electrons away from these two oxygens, which make it pull electrons away from these hydrogens even more than they normally would. So then what happens is that these oxygens pull this pair of electrons away from the hydrogen and then toward itself. Then this makes another bond. And then this bond then gets donated back to the other oxygen because it's pulling on electrons as well. And so what you have is the production of O, C, double O, and H plus and OH minus. When H plus and OH minus get together, what do they make?
Hydroxide.
I already have hydroxide. I have hydroxide and I have H plus. When they come together, what do they make?
Water.
They make water, exactly. So that's the reaction. So is this a balanced reaction that we're looking at? Basically what we're looking at is the reaction goes from 1 to 2 to 3. Are they all balanced?
No.
No? Okay, how do we balance them?
There's 5. Oh wait. Never mind. I miscounted. I think they're balanced.
Oh, they are. Yeah. So this, basically this is an anion. That's bicarbonate. It's basically carbonate with an extra hydrogen. And so this hydrogen leaves and forms this. And then this sodium just moves over here. And then finally, so H2CO3, 1 mole of H2CO3 makes 1 mole of water and 1 mole of CO2. Yeah, so they're all balanced. So if we want to make 1 mole, of CO2 We're starting with this, with our bicarbonate and with our acetic acid. How many moles of bicarbonate and acetic acid are we going to need?
One more for each one.
1 mole of each one, exactly. This is a 1 to 1 to 1 ratio. So yeah, so it makes our math kind of simple. If we just need to calculate how many moles of CO2 it's going to take to fill our 1.2 liter airbag, and then work backwards and figure out then how much acetic acid and how much bicarbonate are we going to need. So let's work out how to do that. So what we're going to need is to get our air pressure. So could someone look up what their air pressure is, where they are? We'll use that as an example.
San Bruno.
Yeah, San Bruno works.
I got 30.12 inches per hg.
Right, so 30.2 inches of mercury. Anyone know how that works? What the hell does inches of mercury have to do with anything? How do we measure pressure in inches of mercury? What's that about? Anyone tell me how that works? You've probably never seen there's actually a instrument in the lab at Skyline that shows you how this works. It's still a working pressure, or a barometer. Well, if you haven't seen one, basically, if you take a column of mercury in a small tube and you pump all the air out on top of it so you have a vacuum, the atmospheric pressure then pushes down on, you have it basically floating in a little pool of mercury. So here you have a tube, there's a vacuum above it, and then it's sitting in a little pool of mercury. Atmospheric pressure then pushes down on the pool of mercury and causes a column to rise up toward the vacuum. And the height of that column is related to how high the atmospheric pressure is. So the greater the atmospheric pressure, the more it pushes down on the pool of mercury, and the more that pool of mercury then pushes that column up. And so basically you're just measuring how high the column of mercury is pushed. And it takes 1 atmosphere of pressure to push a column of mercury 760 millimeters up. So that's why we have that particular way of measuring. So if we have 30.12 inches, how many atmospheres is that going to be? So I want to do the math.
1.01 ATM.
Yeah, it's going to be close. So 1.01.
Mm-hmm.
Okay. So that's our atmospheric pressure. I pretty much knew it was going to be close to 1. So what's the temperature in San Bruno inside right now? Or wherever you might be.
It's 55 outside where I am.
Well, what's it in the room? If you should have your thermometer with you.
Does the
Hopefully it's
thermometer work, does it work instantly, or do you have to like wait a bit?
Well, I mean, no, just it should be whatever. I mean, it's always the temperature of what's around it. So as long as you don't put your hand on it, it should just tell you what the room temperature is.
So yeah, it's about 25.5 degrees Celsius.
Dang, it's hot where you are. You keep your house nice and toasty.
Oh no, I never turn my heater off ever since I
You like the hot, what, man, what the hell are you doing living in the Bay Area? I mean, it's never warm here. Oh, you should move down to SoCal. So
Oh,
25.5. So what's the temperature going to be in Kelvin?
plus 273.5.
0.15.
Oh yeah, 0.15. So that would be 240. No. 298.65.
Right. 0.65 K. So now we're going to calculate N. And it's going to be different depending on where you are. I mean, not everyone keeps their place as hot as Arista does. I mean, my place is always freezing. You know, I'm too cheap to turn the heat on. But so we need to solve for N, right? And when we solve for N, remember N is going to be equal to PV divided by RT. So N, or P, is going to be 1.1 atmospheres, 0.01 atmospheres. V is our 1.2 liter bag that we're going to have. And we're going to divide that by R, which is 0.0821 liter atmosphere mole kelvins, which is still weird to say. And then we multiply that by the temperature. And our temperature is 298.65 K. So our K's cancel. Our liters cancel. Our atmospheres cancel. And we're left with 1 over 1 over moles. So what is 1 over 1 over moles?
Moles.
It's just moles, right? So we're left with moles. So whatever number this is after all of our calculation, we know the unit's going to be moles. So it's 1.01 times 1.2 divided by 0.0821 divided by 298.65. So what is our number of moles?
I got 0.0494.
Okay. So it's 0.0494 moles. So that's how many moles of CO2 should fill up our 1.2 liter bag at 25.5 degrees, where it's nice and toasty, and atmospheric pressure slightly above 1. So now we have our moles of gas that we need. Next, we needed to figure out, okay, if that's the number of moles of CO2 I need to make, how much acetic acid and how much bicarbonate am I going to need? So we move on to the next calculation. So we figure out, since it's a 1-to-1 ratio, right? 1 mole of bicarbonate will make 1 mole of CO2. We need to figure out how many grams of bicarbonate we're going to use. Now, bicarbonate is 84 grams per mole. So we're going to need 0.0494 moles of carbonic acid. We know our molar ratio is 1-to-1, so we don't have to worry. So so moles cancel out. We're left with grams. So how many grams is that?
$4.1496.
4.9146 grams. Now we know we can't measure the mass that accurately. And so what are we going to round that to?
It's actually, I got 4.14.
Oh, sorry, 4.14. 4.1496.
96.
Man, most people, like, they see numbers and they switch them around. I hear them and I switch them around in my head. So same thing. So that's how many grams we need. Now we can't measure it that accurately. So we'll just round that to 4.15. So we need 4.15 grams of sodium bicarbonate. So that's how much we're going to use. So, but the question then becomes, how much acetic acid are we going to need? So you go to acetic acid. Now, I think we actually did this calculation before, where acetic acid is 5% by mass acetic acid in vinegar, right? And then we figured out for every, like, what the molar mass of acetic acid was, figured out the density, and then figured out what the concentration was. So the concentration is given for you, so you don't have to figure it out again. It's 0.833 molar. So what's the easiest way to determine the number of moles we're going to need? Now, I've been looking at some lab reports dealing with solutions, and people are taking molarity and converting it to like grams and all kinds of, using density and all kinds of weird things, which we don't need to do. What's the easiest way to go from molarity to moles?
Multiply by volume.
Yeah, what does molarity mean? What is the actual definition of 0.833 molar, capital M? What does the capital M mean?
Moles of acetic acid per 1 liter of vinegar.
Yeah, it just means moles over liters, right? That's the same thing, moles over liters. So if I want moles, I just multiply by liters. That's all I need to do, because then my liters cancel out and I'm left with moles. So if we need 0.0494 moles, that's going to be equal to 0.833 moles per liter times our volume in liters. So what volume in liters do we need?
Zero 0.0593 liters.
Right, just a little, since it's not, if it was 1 mole per liter, we would need basically 49.4 or 0.0494 liters. It'd be exactly the same. But since it's slightly less than 1 molar, we're going to need a little more. And so 0.0593 liters. But we don't measure in our lab, we don't really measure volume in liters, do we? We don't have a graduated cylinder in liters. What's the unit on the graduated cylinder?
Milliliters.
Milliliters, right. So we got to take this and convert it to milliliters. So I have liters, I want to convert it to milliliters. How am I going to do that? So I need another conversion factor.
Times 1,000 milliliters per 1 liter.
Right, exactly. Oops. Right, so I want milliliters. I don't want to get rid of liters. So I put liters on the bottom. I'm left with milliliters. And so that's 59.3 milliliters, or mils. We normally shorten that too. So that's how much vinegar we're going to need. So we'll need 59.3 mils of vinegar. Yours is, like I said, yours is going to be slightly different. I want everyone's, you're going to need to fill out a data table. So I'll need to see what your atmospheric pressure is and what your temperature is. This is just an example of how to do it. So 59.3. And your answers will be pretty close, but they're not going to be exactly the same. Oops. You go back. Didn't mean to do that. Almost done. Right, so can everyone see the screen again?
Mm-hmm.
All right, good. So here's the data table. So they give you the volume of the bag we're going to be using. You need to measure your room atmospheric pressure, temperature, your calculation for the number of moles. We know it's going to be pretty close to like 0.005, somewhere around there. Right, so your room pressure is going to be around an atmosphere. The room temperature will be around like 295 K, somewhere in that vicinity. So the number of moles would be around 0.05. Balance your equation, give the mass required, mass of sodium bicarb. That's going to be around 4.2 or so, somewhere around there. The volume of vinegar will be around 55 to 60 mils. And then we basically go ahead and do our initial experiment.
The balanced equation is just the one we used initially with the molar ratio, right?
Right, exactly. Yes, you don't even need to do much thinking. I said this was going to be a fairly straightforward experiment. We'd be done if I hadn't just been blathering this whole time. So we just take the balance, weigh out the amount of sodium bicarb. So you do your calculation now, figure out how much you're going to need. And then using the 50 mil graduated cylinder, measure out the amount of vinegar. So you have to measure twice, measure it up to 50 and then up to however more you need. So these resealable bags, they suggest pushing it down on the side of like the beaker. So it sort of makes two separate regions where you can have the vinegar and the bicarb. I had a little trouble doing that. Basically what I did was I just put the bicarb in there and then, or put the vinegar in first and then just threw the bicarb in and then closed it. I mean, either way. You have to do it fast because this reaction happens fast. Not nearly as fast as azide decomposing. That happens really fast. But, it happens fairly quickly. And then just watch the bag inflate. That's pretty much it, really. And then just make some, shake it so that it, you want to seal it. You want to basically, when you add the two ingredients, you want to sort of squeeze the bag so that there's no air in there, and then seal it. Because if you seal it with a bunch of air in there, you've got the air plus the CO2 you're making, and the thing, might explode. So you want to get it as flat as you possibly can. And then you basically dump it out, and then you repeat it using another, using another 1/2 gram of bicarb each time, and an additional 10 mils of vinegar. So the second one, you're going to add another 1/2 gram and another 10. For the third one, you're going to add another gram of sodium bicarb and another 20 mils of vinegar. And you see what happens to the reaction. Does it occur faster? Do you get greater volume? Do you get greater pressure? All these things go into data table 2, where your observations for the first bag you made, the second one, the third one, do they look different? Does the pressure appear greater? Did the reaction happen faster? All those sorts of things. And then basically you end it with, if you were to use this system, and I strongly recommend not using this system for an actual airbag for reasons that will become obvious. If you have the typical driver's side airbag that like inflated in my face is 80 liters in size. And so basically, how much sodium bicarbonate and how much vinegar would you need in order to completely inflate an 80 liter bag at your room temperature and the pressure in your room as well? So data table 3 is for an 80 liter airbag, and I think record all the calculations in data table 4. So that is it. So you can see it's pretty straightforward to do. It's basically all you need to do right now is do that calculation to figure out how much bicarb to start with and how much vinegar to start with, and then get your goggles on, and we'll all come back in about 10 minutes and start the experiment, okay? Any questions?
No.
No, okay. All right. So let you get all your stuff together. I'll get my stuff together. I'm just going to do it the one time because I don't think I have enough vinegar to do it more than once. I've been using a lot of vinegar, both to clean my coffee maker as well as making CO2. So I'm using it for both. Amanda, Lance, there you go. All right. So you can use your plastic spoon in there to measure out the bicarbonate. Hopefully everyone's done their calculation for their particular locale and temperature. Okay. So then you take your bicarb and you basically put that aside and then measure out how much vinegar you're going to need. Hopefully I have enough here. I think I'm probably just going to have enough. There we go. So you could try putting it over. If you move all the vinegar to one side and then introduce a little gap like that, you'll see that the vinegar will stay on one side and you can put the bicarb on the other. That way you can like push most of the air out before sealing it. So I think I'm going to try doing that, although it's a little tricky to do. Yeah, and then try to put the bicarb on the opposite side. Although since you're holding it at an angle, it makes it a little tricky to do. Well, it's working fairly well. Okay, get all the air out and then seal it up. You want to make sure it's good and tight. And so you can see the reaction taking place. It's pretty. So one thing you should notice when you're doing observations, feel the temperature of the bag. That should be telling you something. And when will you know the reaction's over? What observations have people made if they see?
When we're measuring out the vinegar, can we use like both the 50 milliliter and 10 milliliter graduated?
Yeah, certainly. Yeah, actually that'd be more accurate.
Okay, thanks.
Yeah, that's a good idea. That's definitely, you definitely get a more accurate volume that way, because it's kind of trying to measure like 9.2 in a 50 mil is pretty much impossible. So we should notice a couple things fairly readily. What's the temperature of the liquid?
We have to measure that?
No, you won't be able to, but you should be able to see what happens.
Oh,
What does it feel like?
like the vinegar or?
No, the bag, what does it feel like?
Oh, I haven't put the other thing in.
Oh, well, you'll see. Yeah, nothing's happened yet. But during the reaction, you'll be able to tell pretty readily what kind of reaction it is. The other question is, how do you know when the reaction's over? So Jean, have you added the two chemicals together in the bag? You haven't picked the bag up? Pick the bag up, because you're going to need to pick it up to shake it around and make sure that all the reagents, the two reactants mix together. And you should notice something. So everybody else is not doing the experiment today. It's just the four of us. And we got a nice shot of Amanda's ceiling, so can't really see what she's doing. There you are. So Amanda, what does the bag feel like?
It's kind of cold.
Yeah, it is, right?
Yeah,
So
same.
what kind of reaction is that then?
Endothermic?
That's right. It's an endothermic reaction. It's pulling heat from the surroundings and putting it into the reactants,
Wait,
into the products.
these bags, they're not gonna like burst or anything, right? If they get too full of gas, because I'm on carpet.
No, they shouldn't. Yeah, the thing is, you'll notice, so the first one, you'll see that it's inflated, but it's not, if you feel the bag, it's basically not at super high pressure. So the pressure in here should be the same as the atmospheric pressure. But what you should notice that when you start increasing the amount of CO2 gas, that the next bag will inflate a little bit more, then the third one will inflate even more. I think if you like doubled it, it might be too much and the bag would explode, but we're not actually going to double it.
Okay.
Unless you want to. You know, dump an entire box in there and then take the entire bottle and dump that in there. And I think that would be a problem. Yeah, and then you can just pour this down the sink, because basically all you've got now is what's left in here. Anyone tell me what's left in here now? What's in the what's in the bag? What's in the bag?
Water.
Water. And what else?
Sodium acetate.
Water and sodium acetate, exactly. And that should be pretty much it. There'll be a small amount of carbonic acid in here, because remember, that's an equilibrium reaction that goes in both directions. So if there's CO2 in the bag, it's going to react with the water that's in here and form a small amount of carbonic acid, but really, really, really small. So the majority of it is going to be water, sodium ions, and acetate ions. And so that is perfectly fine to put down the sink. Hey, Raj. If we have some vinegar left over, you can do we have any extra vinegar? Check, see if we have any white vinegar. Well, I think I used it all. Oh, we could use the red wine vinegar. That's fine.
Which one?
Is there it should be like in a round bottle. There you go. Here, I'll let you do the next one. So here's your goggles. There you go. So here's the bag. So to open it up, we're going to make carbon dioxide.
Okay.
So measure out about 5 grams of sodium bicarbonate. It's baking soda. About 5 grams. You can use the spoon. Yeah, a little too much. We don't want the bag to explode. Around 5. I'll put another gram in there. There you go. All right. Now we're going to need about 65 milliliters. So fill this up to 50 and then add another 15. We'll start with with this vinegar, and the rest we'll use the red wine.
Okay.
All right, so fill it up to 50 and then 8. Yeah.
This again.
Annie, no. Cool color.
Yeah, it is.
All right, so that goes in the bag. And then put like another 15 or so in the bag. I'll hold it up. First thing is, I don't know what the acetic acid concentration of red wine vinegar is, but we'll still get the reaction.
That's pretty good.
Okay. Now, the next part
That's
is,
terrible.
yeah, it doesn't smell great. So what you're going to want to do is we're going to dump that in here and then close up the bag as quickly as you can. Okay? So
Okay.
dump it in. Then get all the air out and then close it up. Seal, 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 seal. Oh, wow, look at it go. It's pretty in red. You can see the red color makes it really pretty.
Yeah.
So I think that's sealed. So now you just shake it up. Make sure it gets... Now what's happening to the bag?
It's inflating quite a lot.
Quite a lot, right? And what does it feel, warm or cold?
Pretty cold.
Yeah, well, on the bottom. Yeah,
Cold.
pretty cold, right?
Yeah.
Yeah, that means the reaction is taking heat from the surroundings and putting it into products it's making. So yeah, that worked really well. Yeah, so you can see, so we bumped up the amounts here, and you can see the big difference with the bag. It's pretty much almost bursting. So, yeah, just keep, so how will you know when the reaction's over, Roger?
Probably when it stops fizzing.
That's right. That's right. So that's one of the signs of a reaction, is that it makes gas. So when you see the bubbles stop forming, we know it's basically over. There you go. Great job.
There.
Mm-hmm. So we pretty much used exactly the right amounts before this thing explodes.
That would have been quite bad.
That would have been bad. Yeah, and smelly.
Yes.
All right, so does anybody else have any questions about the experiment or what you should be putting in it before we call it a day? You can see it's a pretty straightforward experiment today.
Yeah.
No other questions? All right, so if you have questions about this experiment or the lab reports or anything else, you know, just get a hold of me. I always say, send an email. Come to office hours. Some folks come to office hours. That's always nice. Good luck on your test next week. You're going to crush it. I can tell. If you have any questions about the test too, if you want to review, if you have anything that's confusing you, I'm always available for that too. Whenever you like. Okay.
Thank you.
All right. Have a great afternoon, everyone.
Thank you.
All right. I'll talk to you soon. Bye, Arissa.